Today I'm talking about globular clusters in relation to my previous video, and I'm trying something new. Hope you enjoy. Imagine a puddle of water. As you know, water is made out of molecules, and a puddle of water has a number of molecules that move around somewhat randomly. They move at different speeds, they move in different directions, and some of these water molecules are moving faster than others. Some of them, a small fraction of the most energetic molecules of water, move so fast that they are able to escape the puddle of water. And this is what we intuitively understand to be evaporation. Because not all of the molecules move at the same speed, because some of them are faster than others, some small fraction are able to move fast enough that they float up against the force of gravity and against the force of water tension, keeping the water together. And evaporation is this process by which water molecules can come apart. And this is all by random. This doesn't require you to boil the water by adding energy. And in the process, the puddle of water, all of the water molecules that are left behind, the ones that were not able to escape, their average energy is less because the most energetic water left the puddle. So the water that's left has a smaller energy on average. And we know that the energy of jiggling water molecules is what determines the temperature. So when energy is removed from a puddle of water molecules, the temperature of the water decreases. And we understand this too, because when you step out of the shower, immediately your skin feels cold because the water molecules on your skin are evaporating, taking away energy from your skin because the water is a low temperature. Now this is in the situation where the water molecules cool down. Their temperature decreases when the energy decreases. And somehow we find that to be intuitive. It makes sense that temperature and energy should be related. When something's hot, it should have more energy, and when something is cold, it should have less energy. But what if the opposite were true? Let me introduce the idea of a globular cluster. So a globular cluster is a gravitationally bound set of stars, usually about 1,000,000 of them. And it's important that they are gravitationally bound, because recall from my last video that when something is gravitationally bound, its total energy is negative. Anything that's bound has a negative total energy. And the two components are the kinetic energy, which is positive, and the potential energy, which is negative. And in order for the total energy to be negative, there must be a relationship between the kinetic energy and the potential energy. It turns out that the kinetic energy is about half as large as the potential energy, and the potential energy is negative. So it also turns out that when you have a globular cluster, just like a water puddle, the stars inside the globular cluster are moving around randomly as well. And there are some fast stars and there are some slow stars. And the fast stars are able to escape the globular cluster. Just like in the water puddle, if something has enough energy, it can escape the force of gravity. We know this to be true in the case of rockets, for example. When a rocket has enough energy, it can escape Earth's orbit. So once again, we have this situation where the highest energy things can escape, both from water puddles and from globular clusters. Except in the case of a globular cluster, when you decrease the total energy, that means you make the potential energy more negative. And so that means you actually make the kinetic energy more positive. And the way it works out is that the potential energy more than compensates for the kinetic energy. That is, the kinetic energy gets larger, but the potential energy becomes more negative faster. It's sort of like being wealthy by virtue of being in debt. You can borrow $1 million and now you have $1 million more dollars, which is sort of like kinetic positive energy. But now you have a debt with interest, which is even larger. So your net worth is actually more negative. So it turns out that when the energy of a globular cluster decreases due to the evaporation of some lucky energetic stars, the rest of the stars in the globular cluster have less energy on average. And so the temperature of the globular cluster increases. It's the opposite from the case of the water puddle. And this is because of this relationship in gravity between kinetic energy and potential energy. So what does this mean for globular clusters? For a water puddle, because the temperature decreases as it evaporates, the evaporation doesn't go out of control. It evaporates somewhat slowly until the very last moment when there's almost no water left, but at that point it looks fast simply because there's no water left. In the case of a globular cluster, if you increase the temperature, then that means stars will escape faster. You'll have more stars with a high amount of energy, which will get lucky and escape the cluster. So then the cluster evaporates faster because it has a higher temperature, but that increases its temperature even more. So it just evaporates faster and faster. So you have something called a catastrophe. Hypothetically, at least, you have something called a catastrophe, where you might predict from this naive theory that globular clusters should just evaporate very quickly, because nothing stops their temperatures from going out of control, and nothing stops the stars from all escaping. In practice, we know globular clusters live for a very long time. Many of them are very close to the age of the universe, and I use very close in a proportional way. That is, we know the universe is about 13 or 14 billion years old, and globular clusters are also about 13 to 14 billion years old. At least the oldest ones are. So there must be some way to prevent globular clusters from evaporating, even though we know that by the laws of gravitation, by the laws of physics, as they evaporate, their temperatures increase. So the thing is, we were missing something in our simple description. There was everything we've said so far makes perhaps not intuitive sense, but it makes physical sense. Everything we've said so far is according to the laws of physics, given our assumption that we have 1 million stars in a globular cluster. We must be missing something. So what we are missing is the fact that these stars are not just stars on their own. Some of them are binaries. Some of them naturally form binaries. They come in pairs. And so what happens is, as the globular cluster evaporates and as it shrinks, the stars get closer together in general, and the binaries start interacting with stars close to them. And so what happens is a nearby star will pass by a binary, and what will happen is the binary will donate some energy to the passing star, and therefore increase the average kinetic energy of the cluster. by making some of the stars faster. But it will do this without making the cluster smaller and without making the potential energy of the cluster smaller. Instead, what will happen is it will make the potential energy of the binary smaller. The binary donates its potential energy to keep up the globular cluster. And in so doing, globular clusters are allowed to live for quite a long time because binaries are able to get extremely close, and so there's a lot of energy to be harvested from them. And that's the story of a catastrophe that was averted, the globular cluster core collapse catastrophe.